Guillaume, both for the seminar and also to the department. She's the latest fellow for the Waterloo Center for Astrophysics. We're very happy to have her here. So she's coming to us from UC Santa Cruz, where she just finished her PhD dissertation with Jean Brody and Charlie Conroy. And I think that's a lot of the work she'll be talking about here today. She's actually got an impressive list of awards and fellowship type things that she got during her her graduate career at UC Santa Cruz, including a teaching award. So she really comes with high credentials, and we're excited to have her here in the group. And so she's going to tell us about probing the extremes of galaxy evolution with new stellar population synthesis models. And Alexa, how are you for, are you okay if we interrupt you with questions during your talk, or would you rather hold them all to the end?
I think for today, I'd prefer to hold them for the end, if that's okay.
Yeah, that makes sense. In this format, that can often be easier. So we will do that. So we'll hold questions to the end. Okay, so with that, take it away. Thank you.
Well, thank you. And I just want to thank everybody for coming today and for the opportunity to allow me to give this talk. Given that I'm starting here at Waterloo in very unusual circumstances, I just wanted to have the opportunity to introduce myself and my work and what I'm interested in doing at Waterloo, because I'm very excited to expand my horizons here at Waterloo and work with more people and explore more fields. But today, yeah, I'll mostly be talking about what I did throughout my PhD, and also with an eye to the future and kind of near-term projects I'm interested in, and the kind of instrumentation and that kind of thing I'm looking forward to using and working with. This work wouldn't be possible without a set of really wonderful collaborators. In addition to Charlie and Jean, there's Aaron Romanofsky, who is a professor at San Jose State University, Benjamin Johnson, who is a brilliant researcher at the Harvard CFA, Peter Van Dockum, and Dan Foreman-Mackey, who is opened my eyes to the world of and usefulness of Bayesian statistics, which I'll talk about. The picture here on my title slide is of a Milky Way globular cluster, and it's to foreshadow the point of my talk and kind of the point of my PhD, which is to really proselytize the usefulness of globular clusters, both in terms of understanding star formation mechanisms and galaxy evolution. So I'll just begin with just an introduction to kind of set the scene of why I'm doing what I did and what I'm talking about here. Okay, so in our modern conception of the universe, we think, we see this thing called, we think dark matter halos form in these nodes of the cosmic web, and then galaxies subsequently form in those dark matter halos, and then galaxies then provide the environment for star formation, planet formation, gas, et cetera, et cetera. But the effect and the impact does not only go top down. We also know that there are important ways that the stellar population and the black hole population in galaxies affects the evolution of galaxies. And we also, galaxies are some of our best tracers of dark matter, because obviously we can't see dark matter. And so what this means for us as astronomers is that galaxy evolution is this very interesting field that's on the nexus of a lot of very important physical processes. But because of the just huge physical scales from length and time and distance, it really has stymied our ability to come up with a priori models of galaxy evolution. And so when you're talking about galaxy evolution or star formation or dark matter, I really think you can't treat them independently. You can't know about any one of those. You have to know about all of them to understand these processes, because they're all interrelated. And this is really a blessing and a curse, I think. It's a curse because it makes galaxy evolution a very complicated field to try to wrap our heads around and try to understand. But it is a blessing because we know that all these things, we're getting different constraints from many different avenues, and we know that ultimately they all have to come together, they all have to hang together. And so that is really kind of our most powerful constraint, high level constraint we have when we're trying to understand any one of these processes. And so just to give a brief overview of some big questions in galaxy evolution is, so it's been long established that there's this bimodality in color and morphology, where here I've got on one end the spiral galaxy, which are typically blue because of their young star forming stars, and then on the other end we have these, quote unquote, red and dead elliptical galaxies. They're red because their populations are quiescent, they're just evolving, they have no young populations anymore. And so one of the big questions in galaxy evolution, is why these two forms of galaxies? How and why do we get these, basic two types of galaxies? And this really leads into kind of the other major thing we know about galaxies, is that a lot of their properties follow these very tight scaling relations. And so maybe the most famous or well-known one is the fundamental plane, which relates, the radius of these galaxies, surface brightnesses, and velocity dispersions of elliptical galaxies. But we also know that there's all other kinds of properties of galaxies, both internal and external, that correlate with each other, including globular cluster systems of galaxies and their dark matter halos, there's correlations between black holes and the color metallicity or magnitude relation. And so again, the question is, I just was telling you about how all these very complicated processes go into making galaxies. So it's quite unusual that we find these very tight scaling relations. And so what is really dictating this process, where you go from kind of the disorder of the cosmic web and accretion and the messiness of star formation, and you get in the end, it seems, rather neat ordered properties. And so some basic observational windows to give us insight into these big questions of galaxy evolution are one, these stellar mass functions, where you just count up the mass of galaxies and see as a way to understand how galaxies grow and change over time. And so this started with really Paul Schechter in the 1970s, and now people out of the Go Green survey, led here, are doing even more detailed versions of these stellar mass functions, where you're looking at differences between quiescent galaxies and star-forming galaxies and field galaxies and cluster galaxies, and as a way to understand the processes that affect galaxy evolution and galaxy growth through time. And I'm compelled as a stellar population synthesis modeler to say that these mass functions are really luminosity functions. We don't observe mass, we observe luminosity that we then convert into mass using some kind of model. So another important observational window is the so-called archaeological approach. And so this is where you're looking at the stellar populations within galaxies using their ages or dynamics or chemistry to infer you can really get detailed histories of galaxies in this way, whereas, what I was talking about, where these look-back studies of mass functions of galaxies really give you a broad view and broad constraints. These are very specific to the more minute processes that affect galaxies and their stellar populations. And so right now, I'm just going to walk through an example of how chemistry and our understanding of elemental abundance is important. Just imagine a stellar population that, is born all at once. And then so the most massive stars in that population are going to evolve off the main sequence and then explode as type 2 supernova. And that contributes alpha elements into that population of the gas. It enriches the gas with alpha. But we have yet to have the type 1a supernova go off to enrich with iron metallicity or iron abundance. But then eventually that population catches up, and then you get a dilution of the alpha elements, and you get an increase in the iron peak elements. And so this diagram has been a very useful diagnostic for star formation histories, and we can get a sense based on the overall normalization of this kind of relation of the IMF, because if more massive stars exist in the population, you'll have more type 2 supernova going off, producing more alpha elements. And then also the star formation history comes in really through what's called this knee, this break in this relation. So where this break happens tells us about how quickly or slowly star formation and enrichment was happening in the population. The important thing about this particular diagnostic tool is that this is what is possible when you have resolved stellar populations. So this is what's possible in the Milky Way or the satellites of the Milky Way. Doing this even with Andromeda, it gets very technically difficult, and that with Andromeda, this kind of thing is just starting to really pick up steam, making diagrams like this, just to give you an idea of the range such a particular diagnostic tool can be used. But this has been crucial for understanding the history of the Milky Way and its buildup and satellite populations. And you might have heard about the galactic renaissance, where we are getting just increasingly exquisite data of the Milky Way. And so this is the map of the Milky Way from the Gaia survey. And so now for the Milky Way, we have billions of individual stars that we have, positions and magnitudes and colors for. And then there's even, thousands of spectra of these individual stars from these massive follow-up spectroscopic surveys that are happening. And so with the Milky Way, we're really reaching a point that's very sophisticated, where people are starting to not just give a broad overview of the Milky Way, where, the halo is, likely accreted and the bulge is likely formed in situ, but they're actually being able to trace back, the specific progenitors that are building up the Milky Way and its halo, which is really crucial, because remember what I said at the beginning is, galaxy evolution, we have to understand both how star formation functions, which means we really need to understand the chemistry in these populations, how the populations differ, and then that relates back as a test subsequently to hierarchical assembly. When we get really specific and we get really down into the details of how the stellar halo of the Milky Way built up, does that make sense with the predictions that are coming out of lambda CDM cosmology? And so this is all great. What's happening for the Milky Way is just a massive heroic effort by many people, and it's just beautiful. But I really feel strongly to caution against what I call Milky Way chauvinism, which is, the Milky Way is great, and it's amazing that we have this detailed window into the stellar populations, but the Milky Way is one galaxy, and it's one type of galaxy. And if we really want to get to a point of understanding galaxy evolution, we need to understand the broad spectrum of galaxies. And so that's why in my for my PhD, I really focused on what you might refer to as galactic weirdos. And so to start off with, let's look at this beautiful deep image of the Virgo cluster. And you see some blue galaxies that might be similar to the Milky Way, but then you also see a lot of these red elliptical galaxies. And I'm going to zoom in on and focus on M87, which is the brightest cluster galaxy of the Virgo cluster. And so the Virgo cluster is 16 megaparsecs away, and so we really don't have any hope of getting resolved stellar populations, spectra of resolved stellar populations for M87, at least not right now. And perhaps it'll be very difficult in the future because of crowding effects and so on and so forth. So why would we put in effort for something that we can't, intrinsically we can't understand as well as the Milky Way? Well, one, most of the stellar, the stellar mass in the local universe exists in these kinds of massive early type galaxies, but also these massive early type galaxies are going to be the more stringent test beds for predictions of hierarchical assembly. There's, they've experienced the most assembly, most accretion of satellites, just by virtue of the dense environments that they exist in, and there's a lot of evidence pointing that that kind of assembly is either still ongoing or at least happened very recently. And then also to give a little preview into what I might be talking about later, is these galaxies also have very unusual stellar population properties. So we really need to understand these galaxies and the differences between these kinds of galaxies and galaxies like the Milky Way or Andromeda, and what is dictating these differences between these kinds of galaxies. And so when you're at this distance, when you're trying to look at a galaxy 16 megaparsecs away and understand it and use the archaeological approach, what you have access to is an integrated spectra. So if you remember my little cartoon of the stars and the alpha abundances, just imagine averaging all of that together and just getting one spectra instead of individual spectra of the stars. And this is what I'm showing here. This is a very high signal to noise spectrum for M87. And so all through this talk, I'm going to be talking about precision stellar population synthesis modeling, where we are fitting the absorption lines of spectra like this. This is not SED fitting, where I'm fitting like the shape based on photometry, and it's not index fitting. And if you want to ask me at the end why those differences are important, I welcome you to. But the key point is that this spectrum, all these little squiggles and shapes you see in the spectrum is real information about M87. It holds real information from its age to iron metallicity, alpha abundances, C, N, there's a lot of information encoded in the spectrum. And so it's my job as a stellar population modeler to try to figure that out and unwrap that. And by doing that, the idea is we can understand the history of M87 and galaxies like it. Okay, so the question then is, what do we know when we look at these kinds of integrated spectra? And so here on the left, I'm showing this is now for a set of these massive early type galaxies similar to M87, where it's the stellar, it's the velocity dispersion versus the magnesium abundance for these galaxies. And this is fit for various different stellar population codes. And while the normalization might be a little different between the different codes for the magnesium abundance, what you're seeing is that with increasing velocity dispersion, the magnesium abundance increases in these galaxies. Velocity dispersion is, of course, a proxy for mass in these galaxies. So the takeaway here is that the most massive galaxies have this very quick, very early star formation. And 15 years ago now, Daniel Thomas put that together in a model to make this little cartoon that I'm showing on the right here, where it's rate of star formation versus look back time. And so this is just another way to emphasize it, where the most massive galaxies, the width, the width of these Gaussians is really the length of the star formation. So the most massive galaxies form their stars very early, very quickly. They got magnesium enhanced relative to iron in the similar process, like I described before for the resolved populations. And so this was a very surprising result. This was very strange, and it was given many names. You know, anti-hierarchical behavior, because why would these massive galaxies form so early, or downsizing. You know, astronomers give these terrible names to all kinds of processes, and this is what it is, because it kind of on the face flies against our expectations of how we think galaxies should form and then assemble based on the lambda CDM paradigm. And the way people have kind of wriggled out of this issue here is that these measurements, you know, these magnesium measurements that I'm showing here, are really happening in just the very innermost region of these massive early type galaxies. So it's really just the central core that's being measured when we're getting integrated light. We're not getting to the edges. And so the way around this being anti-hierarchical is that, you know, this core formed very early, and then, you know, subsequent merging events and accretion events then formed out, and we're just not reaching those kinds of those populations when we look at integrated spectra like this. And so that is an idea, and ideas need to be tested with observations. And so the thing you need to test that particular idea is not just integrated measurements, but spatially resolved measurements of stellar populations of these galaxies. And so these, you know, shorthand is just calling them stellar population gradients. And so this is something that really, getting stellar population gradients of extragalactic systems and massive early type galaxies is really relatively a novel thing, basically because integrated field unit spectrographs had to reach maturity before people could get enough data of high enough quality to make these measurements beyond the cores of these galaxies. If you look at this image I'm showing of this is again M87 now from Chris Mijos's imaging survey of the Virgo cluster, you can see that there's just a precipitous decline in surface brightness from the centers of these galaxies. So it's challenging to get spatially resolved spectroscopy where you can measure stellar population gradients. But IFUs are coming online. They've been online now for a while. And so now we're starting to see emergence of all these different surveys trying to look at stellar populations and trying to test our understanding and constrain our understanding of how did the stellar populations in massive early type galaxies originally come into place, and then how did the subsequent assembly happen. And so one particular survey is the MASSIVE survey led by Cheng-Pei Ma and Jenny Green. Other surveys, of course, are the MANGA survey that's also been doing great work in this respect. And so here I'm just showing an example of a result from the MASSIVE survey of applying, this is now Lick indices, to spatially resolved spectroscopy of massive early type galaxies, looking so now we're not looking at a singular value of Fe versus alpha for these galaxies. Now we can separate that and see how it changes with radius. And so this is great. This is great work. But there's still an issue that I have to talk about, which is even with you know, really good IFU instruments, the extent of the spectroscopy for surveys like this is typically, you know, at most out to 2.5 RE. And now, so M87 is not included in the MASSIVE survey, but I'll just quote what 2.5 RE is on this image I have of M87. So it's still quite a small area. And so let me explain what the issue is here. So this is the same image as before with the 2.5 RE highlighted here. So this, I'm going to call this the inner halo of M87. And we kind of know from cosmological simulations, and it also, observationally makes sense that the inner halo region is going to actually be a complex mix of in situ and ex situ stars. So this makes integrated light difficult to interpret. And you can think through why. The whole premise of, galactic archaeology, extragalactic archaeology, is that we can infer the histories of galaxies by looking at their stellar populations. But what if you're not looking at a single population of stars that all came from the same process? What if you're looking at and measuring, in fact, the average of at least two populations that formed under different circumstances? What are you really able to understand from integrated light alone, from, with that, keeping that in mind? So really, it's this outer halo region, and I hope you can see this on your screens, where this, M87 has this big extended stellar halo that you see in these deep imaging surveys. And so it's really going to be this outer halo region that is the cleanest test of, assembly predictions. But again, the problem of, declining surface brightness, it's just going to get worse and worse and worse. And so getting spectroscopy, once again, of this, outer region that I'm highlighting in this green box, very difficult, very, not currently feasible. And so one way people in the past have gotten around this is using globular cluster systems of galaxies as these discrete tracers of the halos of galaxies. And discrete tracers, just kind of a buzzword that's kind of wrapping in a lot of meaning in a very succinct term, which is just like I mentioned earlier, that there's all these scaling relations between globular cluster systems and galaxy properties. And so there's really well-motivated evidence that globular cluster systems do trace on some level, star formation events in galaxies. Globular cluster systems are ubiquitous, above a certain, pretty low stellar mass. And so they can really be used to, when a galaxy like M87 accretes a satellite galaxy, it's also accreting its globular cluster system. So here now in this image of M87, I'm just highlighting the catalog of globular clusters from the Next Generation Virgo Cluster Survey. And so these globular cluster systems are useful in several ways. One, they overlap with coverage of the galaxy's starlight. GCs are about as close to simple stellar populations as we can get, but put that in your pocket for later, because I'm going to talk about why that isn't quite right, and how to move past that in a more informative way. And then also, as you can see, globular clusters allow us to extend coverage to the outer halo. So globular clusters are very dense, and so they're going to be brighter than the underlying stellar halo that they occupy. And furthermore, globular clusters are old. Exactly how old they are is very uncertain. But again, the fact that we know them to be just an old population is very useful for us, because, any archaeologist, whether you're Indiana Jones or, me, archaeology is premised on having fossil records. And when you have old fossil records, then what you're really getting is a long memory of both the assembly history and the very early star formation in these galaxies. And so this is all kind of the motivation for why people want to use globular clusters to trace galaxy evolution like this. And this has, motivated huge investments in photometric surveys of GC systems. So the Next Generation Virgo Cluster Survey was on CFHT. There've been, a bunch of GC surveys, led by people like Bill Harris, on HST even. But again, the issue here and I've alluded to this, is that GC formation is still a major unsolved problem in astrophysics. And so we're using a set of objects that we don't really understand as proxies for this galaxy evolution and star formation process. And so what this has done is, when we rely on photometric surveys, this really roots extragalactic GC studies in assumptions that we realize are causing problems for us. So let me explain and unpack that a bit. What is exactly the issue? So, like I said, many surveys of GC systems around galaxies, and one of the, tools people like to use for extragalactic GC studies is make histograms of the color distribution of the GC system. And so this is the result of the ACS-VCS survey. This is Eric Peng's paper from 2006. And these different lines are different bins of galaxies, the color distributions of the GC systems for galaxies at different magnitudes. And so they were not the first people to demonstrate this, but they did it very systematically and very nicely. And what they found is that these peaks you're seeing in this color distribution, that's referred to as bimodality of the GC systems. And this seems to be a fundamental property of these systems in massive galaxies. And there was a lot of back and forth about whether this meant that, did these galaxies experience 2 epochs of major star formation? But currently the consensus is kind of that the blue GCs are supposed to trace the accreted population. So the blue GCs that we see around these massive galaxies are predominantly from satellite galaxies. So they're lower mass, so they're lower metallicity, and then they came into the system. And that's also motivated by the fact that we predominantly find these blue GCs in the outer halo, while the red GCs, which are supposed to trace the in situ formation of a galaxy, really peter out as you go out in extragalactic radius. And so I mentioned these scaling relations that people use between galaxies and globular cluster systems. And so this is an example of what comes out of something like this. So now I'm showing on the x-axis galaxy luminosity. So we've got dwarfs to giants, and then mean color of the GC system subpopulation. So this is this is the same data that I showed here. And so now basically taking the peaks of these color distributions and then plotting them against galaxy luminosity. And people like to use these kinds of relations to infer very important things astrophysically, star formation epochs, the mass of the progenitor satellites, which is, 2 things that are predictions that come out of cosmological simulations, for example. But of course, it's not color that's useful for this kind of inference. It's actually metallicity. And once again, we don't observe metallicity, we model it. And for most extragalactic globular cluster systems, people use these color metallicity relations to transform GC colors into metallicities. And this is all premised on globular clusters being very close to simple stellar populations, being old, and then also, most importantly, the kind of globular clusters we see are all kind of clones of the globular clusters we know so well from the Milky Way system. But these color metallicity relations, and I don't want to get into the weeds too much, have just been a huge source of controversy within globular cluster communities. Some people question whether bimodality is even real. But in the ACS-VCS survey, you developed a color metallicity relation that they used to transform their colors here into metallicities. And you can see that it's this broken power law relation. But the important thing here is that, once again, this relation was premised on the idea that all kind of globular clusters, are kind of the same, and they're kind of like Milky Way globular clusters, or very similar to Milky Way globular clusters. And so there's been this real lack of spectroscopically derived metallicity measurements for representative samples of extragalactic GC systems. And so what the ACS-VCS survey had to do in this paper is they had to supplement their sample that they used to derive this color metallicity relation with Milky Way GCs, predominantly at the blue metal pore end. And, you know, under conventional understanding of globular clusters, shouldn't be an issue, right? And so, but one thing that I really worked on early in my PhD is trying to develop full spectrum synthesis, stellar population synthesis models that go to much lower metallicity than was previously feasible. And because, you know, the inference of detailed stellar population information for GCs has really been held back by limitations in these SPS models. And this is just a cartoon to demonstrate. So these full spectrum SPS models were designed originally to measure populations in the cores of massive early type galaxies, which are fairly metal rich. And you can see that in this blue box. And then just to show you the range of globular cluster system metallicity just for the M31 GCs, you can see how limiting that is. And you know, it's not just limiting for globular clusters, there's a whole metal pore universe. In fact, there are more dwarf galaxies than massive galaxies that really couldn't have their, you know, as detailed information extracted from them before I did my first major work, which was developing these full spectrum stellar population models with expanded metallicity coverage and expanded wavelength coverage. So here I'm just showing most stellar population synthesis models are based on the Mila stellar library, which has great stellar parameter coverage. You can see just in its range of metallicity, you know, this is individual stars. Now this is stellar spectral library. It's metallicities, but the Mila library is a optical library. So it ends here, you know, in that gray line on the spectrum plot. The stellar population models that, you know, Charlie Conroy originally made were based on this IRTF library published back in 2009, which extended the coverage to the near infrared, but very limited in scope in its metallicity range. And you can see that in the black histogram here. And so that was the state of the art until I started my PhD and worked on this project and developed these models with Charlie. And so everybody loves a GIF, so I like to put this GIF in just because it's a good demonstration. You know, this is not just use this library along with the Mila's library to make this data-driven model where we can generate stellar atmosphere spectra from basic stellar parameters, metallicity, surface gravity, temperature. And this is the basis along with mist isochrones that we use to build the models. And I don't have time to get into the details of the model, but again, you can ask questions for me after the talk, or also you can ask them to me whenever. But what this new stellar population modeling allowed me to do is actually take and measure a really large sample of globular cluster spectra and extract these stellar iron metallicities for individual GCs for the M87 system. And so this is what I'm showing here in the gray. So this is individual GC color versus individual GC metallicity. And so here I'm showing in the gray points my purely empirical, only M87 GCs included color metallicity relation for M87. To allow you to understand what's happening here and why this is important, I'm also showing the ping relation here in dashed line. And I'm also showing the color metallicity relation for the Milky Way globular clusters, which remember, Peng had to use, and, you know, had to supplement for their color metallicity relation for the ACS-DCS survey. And so the surprising result that came out of this is, you know, at fixed low metallicity, the Milky Way GCs are redder than the M87 GCs, which is not expected under the conventional wisdom of extragalactic globular clusters, that they should be very similar. They should have the same internal physics information as Milky Way. So there's some difference that's affecting the metal pore populations between the Milky Way and M87 globular cluster populations. In terms of constraints on galaxy evolution, this makes a substantial difference on the metal pore scaling relation. So again, I'm showing you the same relation that I showed you before. The dashed lines are from ACS VCS, and now the solid lines are where I took the ACS VCS photometry and just used my color metallicity relations to transform the scales, and you can see the substantial difference this makes for the metal pore GCs. And so if you're interested in timing star formation epochs or assembly epochs, or if you care about the ages of metal pore GCs and how they relate possibly to reionization, for example, this should be very troubling to you, because this indicates that we don't understand something fundamental about the internal processes of these objects. And this is really important to understand because, you know, there's the next generation telescopes between the Vera C. Rubin Observatory, Euclid, Nancy Grace Roman Telescope. We are on the cusp of volume-limited samples of GC systems. So we're going to get a lot of photometry of GC systems. And that's not even to speak to all the archival, you know, HST, CFHT, you know, imaging data that already exists that might be being used as metallicity calibrators, but might have the serious accuracy problem with the metallicity. And so we need a means to calibrate this photometry. And so, you know, the question is, well, what is driving this difference between the Milky Way GCs and the M87 metal pore GCs? Is it horizontal branch population? Is there some different enrichment mechanism where the M87 GCs are forming these more populous blue horizontal populations than the Milky Way GCs? Is it an age difference? That would be very significant. And we're still very limited in the actual spectroscopically derived metallicities we understand for extragalactic GCs. And we need to know this. We need to understand the internal physics of GCs much better in order to properly calibrate photometry, and then also just use them as tracers of galaxy assembly. And the good news is there's just thousands of archival GC spectra that have never been modeled with modern SPS models, and maybe have never been modeled with any kind of SPS model, because prior to the development of full spectrum models, the signal to noise of this data just wasn't sufficient. So there's all this data that was used to derive kinematics, which is actually what the M87 sample was originally for. It took the development of my models to actually be able to fit accurately and infer stellar metallicities from those GCs. And so we really have an opportunity to make a lot of progress with models that already exist and data that already exists and just needs to be reproduced and then fit with the new models. So just a little plug, I would say this is a very good student project. So if any faculty here have a student that might be well suited for this or might be interested or working in an overlapping field, or if any student is interested in this, it touches upon galaxy assembly, but then it also touches upon very important internal physics, which just briefly, if it's a horizontal branch thing, that would really relate and possibly be very informative to the multiple stellar population parameter problem that we see in the local group clusters. So this might be a way to add additional information for that problem too. So this could potentially be a very high impact project that I just think would be great for a student. So anybody interested, please be in touch. But moving on, because I developed all these great, I do think, photometry is going to be great. We just need calibrators, no point in throwing the baby out with the bathwater. But ultimately, my heart is in spectroscopy. And so what I was able to do with these developed models is fit just a huge sample of globular clusters around M87. So using all archival data, so I'm showing LRES, this MMT spectra, the outer halo. So this is showing spectroscopically derived FE over H versus projected galactocentric distance from the center of galaxy, M87. And so this is huge. This is nearly 400 individual stellar metallicities of the GCs around M87 to quite a large radial range, over 100 megaparsecs. And so I told you earlier about how important and the stellar population gradients of galaxies is, but all the limitations, and GC populations are a way to add additional information, an additional tracer of this formation. But once again, the metallicity gradients of entire GC systems is not very useful, because we know to some level that is, especially around massive galaxies, GC systems are aggregate populations that came in from different formation mechanisms. And so we really need to split up the subpopulation and then measure properties in order to be astrophysically useful to us. And people have done this. People have looked at, there have been studies that have looked at, the blue gradient versus the red gradient of GC systems. And so this plot is kind of a summary of a meta-analysis from Duncan Forbes and Remus in 2018. But I want to draw your attention to a specific feature of this plot. So it's plotting the gradients of the blue subpopulation versus the red subpopulation, and it's many different studies. The same color point indicates when it's the same system studied by different people. It's a different paper. So you might see the immediate issue here, which is there's a terrible accuracy issue where many of these different studies on the same GC system don't agree at all with these gradients. And so if you're trying to build up a systematic sample of gradients that you can then potentially compare to simulations or just make empirical inferences about it, this accuracy issue really is a huge problem. So why? What is the reason behind this accuracy issue? So first, one major contributor of uncertainty is the fact that the distances we measure are projected distances. But of course, that's only a noisy representation of the true 3D distances of the globular clusters. And I'm just showing for different slopes, this is just mock data, how the true 3D distance gets converted into projected distance. And you can't know ahead of time what your slope is to try to do some kind of correction for that uncertainty. That's putting the cart before the horse. It doesn't make sense. Furthermore, we have these GC systems, and we know that they are made up of subpopulations of different origins, but there's nothing, on high telling us which individual GC goes into which subpopulation. And so there's a covariance between any measurement we make on the subpopulation, so for example, in this case, slope, and how we assign globular clusters to that subpopulation. And so what people have done before is they just make cuts. They'll plot up the color distribution like I showed you earlier, and then make a cut, or they'll try to do more sophisticated things, but it always comes down to making a cut on subpopulation and then measuring properties of that subpopulation. And when you do that, you're introducing bias into your measurement because you're not accounting for that covariance. And so I'll just show an example of this. So this is all mock data for different, two different subpopulations that I'm showing in the blue and red in each panel, different slopes that were generated here. And then in the black, and this is multiple iterations of mock data, and then in black, I'm showing what we would see if we were just observing this. So this is just like the metallicity distribution as a whole. And so I took this mock data and I processed it like people prior to me have processed it, make a cut, then make a measurement. And then I can see how much this process biases my answer away from the truth that I know. And the result is it biases the answer significantly and in a way that is dependent on the underlying slope. So these two things are really the major sources of uncertainty of being able to separate GCs into subpopulations and then measure properties of those subpopulations in an astrophysically useful way. So what I did in a recent paper of mine is developed a hierarchical Bayesian model that mitigates the effect of these uncertainties. Now, I encourage you, if you're interested in hierarchical modeling or this strikes your interest, I encourage you to read the paper. This is too much to go in this talk right now. What I'm showing here is called a probabilistic graphic model. And so this shows all my parameters of my model and the data of my model. So the data is represented in the gradient circles. And so I've got the galactic centric radius, I've got my measured metallicities, and I've got my uncertainty on the metallicities. And then the arrows indicate the direction of the relationship between all these parameters. And so this is complicated, and so I'm just going to draw your eye and your attention to a few salient features of this model. So one, Bayesian modeling allows us to marginalize over unobserved parameters. And so this allows us to take, so in this specific case of gradients of GC subpopulations, this means by placing a prior on the scale length of the GC subpopulations, we can marginalize over the 3D true distance distribution. And so this allows us to take into account that source of uncertainty in this specific instance. Furthermore, I can simultaneously fit for subpopulation memberships, which is indicated by this Q parameter, and the gradient properties that I'm trying to measure. So this is the slope and the intercept of the gradient. And so by creating this model, I'm taking those major sources of uncertainty in measuring gradients of GC subpopulations around massive galaxies, and I'm accounting for them and mitigating them in the model. And so the result of this is now we can see the metallicities of the GCs. Now this is showing deprojected galactic center distance. And so these points are all the data points that I showed you previously. The colors of the data points are colored by their subpopulation membership. So there's the metal, so I assumed by modality in this model. So there's the metal rich indicated by the orange, and there's the metal poor indicated by the blue. And the opacity of the points indicates the certainty of that subpopulation membership assignment. And then in these bands, I'm showing the best fit, really the median of the posterior and the 1 sigma errors of the gradients we measure. So it's pretty complicated. So I'll step through it and start with just here, the inner halo globular clusters. So the surprising thing about this inner halo GC subpopulation and their gradients is the remarkably flat metallicity gradients for both the metal rich and the metal poor GC subpopulations. So we kind of understand why that would be the case for red GCs. Major-ish mergers could bring in metal-rich GCs, disrupt and mix in with the in situ metal-rich GCs, and that could lead to a flattening gradient. But for the metal-poor GCs, they're supposed to be predominantly coming in from accreted satellite galaxies. And we understand from just how dynamical friction works that minor mergers like that should lead to a negative metallicity gradient. So it's very unusual, this flat metallicity gradient for the metal poor GCs. And so one possibility is, well, did all the low mass satellites accrete very early before the major mergers? And tentatively, I'm going to say it doesn't seem likely that that is the case, because I also have spatially resolved stellar population gradients of the M87 starlight, so the galaxy itself. And we see that this has a gradient. So if all the low mass satellites came in early, we'd expect the stellar metallicity gradient to be similarly flat, and it isn't. And so just to reiterate a point, this is why it's very important to have multiple tracers of an inner halo population, because you can use them jointly and to inform on how we should be interpreting either thing. So, okay, so what's the deal here? Another explanation is that there is an accreted metal poor GC population that is being diluted by an in situ metal poor GC population. And so the motivation for this explanation comes from the work of Nir Mendeleker, who's a great cosmological simulator, really works with, does wonderful things with cold gas filaments at high redshift. He's currently a KIT postdoc in Santa Barbara, but when he was a postdoc at Yale a few years ago, he came up with this model of in situ metal poor GC formation that forms these metal poor GCs directly in the halos of massive galaxies. And so the key thing, and it's how these stellar cold gas filaments fragment as they come onto the galaxy. And so the key point of this model is that the GCs formed in this way would have flat metallicity gradients because there's so little metallicity evolution at the redshift of these simulations, which is about Z6 to 3. So this is very intriguing possibility. And if we could confirm that there is this in situ metal poor GC population in these massive early tech galaxies, that would open an unprecedented window into both how what was going on at the high redshift IGM and also the very early star formation epoch of these massive galaxies, which we really don't have good access to or clear access to right now. And so, people can ask me about the IMF, and also we know that there's other weird things happening in the course of these early tech galaxies. So having a fossil record of the very early star formation would be very compelling, in my opinion. And so Nir and I are currently working to look into his simulations to develop diagnostic tools of the globular cluster systems to verify and falsify different GC formation scenarios, including his own. And this is very important because GCs are starting to come into cosmological simulations. The FIRE group is very close to actually being able to resolve the formation of GCs directly. The eMosaics group they don't resolve, but they do a kind of a semi-analytical model thing, and they're starting to they're using their model of GCs to make inferences about particular the Milky Way and the accretion events that led to that. And so we need to develop tools to test these formation scenarios in any of these models. And so that's really where spectroscopy is going to shine in extragalactic globular cluster studies. And so one thing that I'm hoping to do, that I'm really eager to do as a fellow here, is extend my hierarchical model that I'm currently using to measure gradients, but I can extend it to measure alpha versus FE without needing to stack any spectra. And so this is just a simplified version of the probabilistic graphic model again, and it's just to show you how I can extend the model, because I do get very noisy measurements of alpha elements from the individual spectra, and one of the strengths of this hierarchical modeling is using the fact that these different subpopulations should all be coming from the same origin. We can use that to denoise the measurement. And so right now I'm calling this kind of the quasi-resolved means to get regime. And so we can't make plots like this from integrated starlight of extragalactic galaxies, but we could make an analog plot for GC subpopulations for these galaxies. And so we can see how the different subpopulations of the GCs, how their relationship of alpha and iron metallicity change from one another, which would be very useful for constraining assembly. But again, it's establishing this very unique window to the very early star formation processes of these galaxies. And once more, maybe somebody out in the audience is being like, well, why is it bimodality? Like, why that? And I agree. I think it's time to move past bimodality. The reason why, there's nothing about my model as it is now, even for the just the metallicity gradients, that requires an assumption of bimodality. The limiting factor is just how little information we have to inform how subpopulations should break up more precisely. And so another thing that I'm eager to work on as a fellow here is the problem with GC ages for extragalactic and integrated light is this degeneracy between the blue horizontal branch and the ages. But I think the models, the stellar population models, can be developed with this in mind to help break that degeneracy. And then there's also people like Chris Usher, who is a postdoc in Sweden now, working with Angela Adamo, is I think going to be working on that says making more CMDs and moving beyond the Milky Way, where we have resolved CMD diagrams. So the point here is that if I can break this degeneracy that really blocks our path to getting absolute ages of these GCs, then that can be an additional constraint on the hierarchical model, which will allow us to move beyond bimodality and actually start thinking about, you know, not assuming the number of subpopulations, but actually letting the data tell us how many subpopulations there are. And
Alexis,
so,
sorry, can I just interrupt a second, just to let you know that we're a little bit over time already, so
oh, sorry.
we have another meeting.
I'm gonna wrap up soon. Sorry.
Okay, yeah, it's fine. Sorry to interrupt.
So just let me get through this quickly. I'm almost done. So there's also this outer halo here that for M87 and for I think a lot of, you know, this is the first spectroscopically derived metallicity of the outer halo of massive early type galaxy. And from the mass metallicity relation, we can infer that the satellites that should be building up this halo, this outer halo, are about 10 to the 8. So, you know, very small, or very low mass. This is in tension with what current cosmological simulations are saying, which is that it's really, so this is from the TNG, so this is halo mass. I've highlighted kind of the region you'd expect M87 to be. And then this is minimum progenitor stellar mass of the accreted satellites that came in. And so what illustrious TNG and other cosmological simulations are saying is that it's really Milky Way mass galaxies that should be making up the outer stellar halos of these massive early type galaxies, which is in contradiction to the observational constraints. It's not just the stellar populations, the metallicities, the GC population counts are also discrepant here. And so, you know, the M87 halo cannot be explained by just shredding a bunch of M31s or Milky Ways, as far as we understand them present day. So is there something wrong with the simulations? Or is there something where the surviving population is different from the accreted population? And so this is just recently a new type of galaxy, or maybe a new type of galaxy, the ultra diffuse galaxies were discovered. And the big deal with them was, I'm showing a size, a magnitude size plot here of various objects. And so what you see in these UDGs is that they have the sizes of giant galaxies, but the luminosities of dwarf galaxies. And so people got really excited about this at first. You know, they're failed Milky Way galaxies, and so they've got all these properties of interesting dark matter. And they could potentially help, you know, plug this gap, this discrepancy between the current observational constraints and the simulations for outer halos. But the problem is there's still significant, you know, controversy about whether UDGs are just belong to the canonical dwarf population or not. And most, you know, people making UDG formation scenarios are saying we don't need any revision to our understanding of galaxy evolution, and they are just dwarf galaxies that got puffed up with these just weird mechanisms that are totally normal. And so, one galaxy, UDG in particular, is DF44, which is really held up as potentially a prototype of a truly failed galaxy because of its very populous GC system and its high measured stellar velocity dispersion, which indicates that it has this massive halo. more recent paper that I'm working on is really comparing DF44, which I now have these very exquisite measurements for, to the normal dwarf population. So here I'm just showing the mass metallicity relation for local group dwarfs and coma dwarfs. And you can see that the two populations kind of create this very, they're scattered, but it's definitely a relation. When we put the UDGs on, we see that there's large scatter above and below this mass metallicity relation. But UDGs, they're intrinsically low surface brightness, so this is just a result of imprecise measurements. And so I'll just highlight an old measurement of DF44 in this plot. But now what I have is very high signal to noise spectroscopy for DF44 from the Keck Cosmic Web Imager. And we see very definitively that DF44 falls below the mass metallicity relation established by the canonical dwarf population. And so, is there some unusually catastrophic quenching mechanism such that once it was quenched, no vestigial star formation could happen, is one possibility. And so just going back again to the spatially resolved spectroscopy, the KCWI is so high signal to noise that we could actually break it up into apertures and get spatially resolved gradients for the first time for any UDG. So I'll just go quickly through this. We measure a flat age gradient, kind of positive to flat metallicity gradient, and a declining magnesium gradient for DF44. And this is really, these gradients are very inconsistent with both observations and predictions of formation of canonical dwarfs. So this is, both the gradients and the mass metallicity relation are indicating that DF44 is not consistent with canonical dwarfs, either in the Milky Way or in clusters, including the coma. Another interesting aspect of DF44 is that the inner part of DF44 really matches with metal poor GCs in abundant space. And this could potentially tell us clues of how to time star formation for DF44 and the quenching epoch. But we don't have the observations right now to say this, to make an apples to apples comparison between DF44's field population and its GC population. So I'd really like a way to be able to push the boundaries and do the kind of analysis I did with M87, where I jointly analyzed the field population with the globular cluster population for DF44 and other UDGs. But coma cluster is 100 megaparsecs away, while Virgo is 16 megaparsecs away. So I'm very excited about these large spectroscopic survey telescopes like the Mauna Kea Spectroscopic Explorer that are coming online. So I'd be interested in talking to somebody about that as an application for such a telescope. I'd be remiss to not talk about the James Webb Space Telescope. These new models that I talked about here are really optimal for the forthcoming IR multi-object spectrograph on JWST. GCs are really important. And then just final, to go back to my schematic, here's where I really spent my PhD, but I'm really looking forward to, during my time at Waterloo, to go towards this side of the diagram and really expand what I've already done and all my thinking. So thanks, and I'm really sorry for going over time.
It's okay, thank you, Alexa. Thank you. Really cool stuff, very interesting. We have our virtual applause. We are well over time, and I in particular have to go. I'm late for another meeting, but that does, if you have questions and you want to hang around on Teams, the nice thing here is that the virtual chat can stay open, so you can discuss, but also Alexa's around. So I think, this is great to have you here. And
yeah, I'm around, and I would love to hear from people. So, feel free to email me. I'm happy to set up chats or whatever.
So there are some questions in the chat here. Mike just asked a question about if your stellar library has high alpha, high metallicity stars. I'm going to have to go, but I will leave you to the questions. I really apologize, but I do have to run.
I'm sorry for going over. Thank you, Michael. I can't see the chat right now.
I can just repeat the question was, in the Milky Way, usually the high alpha stars, that you would put in your library are low metallicity, right? Like in the diagram that you showed. But giant ellipticals tend to be high metallicity and high alpha at the same time. So I don't know how
So
that problem is tackled.
yeah, so the way that problem is tackled when you're using empirical stellar libraries is we make what are called response functions, element response functions, where we can correct for the underlying abundance patterns in the stellar library. And so we can talk more detail about that offline, but as also all the details in that are in the Conroy-Viome 2018 paper as well.
So it's similar, I think, to the Thomas et al. Approaches from earlier, right?
Yeah, the big change with these models from Thomas et al. Is one, the move from index-based measurements to full spectrum measurements, and also the inclusion of more elemental abundances that we have response functions for.
I.e. not just alpha, right?
Not just alpha, C, N, there's other more exotic elements. Yeah, so, you know, some R process elements, S process elements, that kind of thing. Any other questions? Oh, here's how I get the chat up. Oh.
Just ask people to fire away.
Oh yeah, so James Taylor said, could alpha enhancement explain the colors of the M87 GCs? No, it is not a large enough effect. I did test for that. It's really, I think it either comes down to age, which I think is really unlikely because that would mean the metal poor M87 GCs would have to be 40 years younger than the Milky Way metal poor GCs, which is, you know, stretches credulity for me. So I really suspect it's coming down to some horizontal branch process where these M87 GCs for some reason are making more populous blue horizontal branch populations that is causing them to be bluer than the Milky Way populations at similar metallicity. And so that's why it's so interesting, because the blue horizontal branch, or the horizontal branch in general, just connects to so many very important internal formation processes for GCs, like the multiple population problem that we currently see in the local group GCs.
Just in a follow-on to that, I mean, does anyone ever think that the binary populations or fractions in these systems could be different? I mean, that close binary interactions could drive any of this stuff?
So I'd have to think about that. My first thought in response to that is I'm not sure at these ages, the globular clusters, is that even a difference in the binary population would make much of a difference in these observed colors between the Milky Way and M87 GCs. But it is an interesting point, and I can think more about it for sure.
Could I jump in there, James, as a potential? We have a new grad student working on just that question. The close binary massive star interactions are capable of generating the kind of internal differences in chemical abundances that we see in massive star clusters. And it's going to require a lot of new modeling to make that all specific and quantitative, but it's underway.
Bill, I hope we can get a chance to talk more about that. I'd be very interested to hear about that.
You
Okay.
count on it.
Okay, great.
Because we're always hearing about intermediate mass black holes being made by all these binary interactions in globular clusters. So,
the key thing is that that we're already finding in early stages of these new simulations that are running is that yes, indeed, binaries are there and they form rapidly, and they're already fully in action in the same initial few megayear period where there's a lot of gas still present. So it's promising. A whole lot of actions happening in the first few megayears of a massive star cluster.
I see that I missed a question at the beginning of the chat thread. by, please correct me if I'm pronouncing this wrong, Niesh Afajordi.
I just repeated the question that you suggested. What about the IMF?
Yeah, it's great. What about the IMF? So
I think you were talking in particular about this new channel of formation that I think someone proposed, the simulator proposed. So I think it was another slide you talked about IMF. Well, you told us to ask you about IMF.
Yeah. So I had a whole project, the paper that I didn't have time to talk about in this talk about the IMF, where it's very a muddled situation right now, what's going on, because when you look just at early type galaxies, people are thinking that the primary driver of IMF variability is metallicity. But what I was able to do is measure the IMF for what I call, the umbrella term is compact stellar objects. So this includes globular clusters, but also ultra-compact dwarfs and compact ellipticals. And so what you see when you expand the parameter space beyond like the relatively very narrow parameter space of massive early type galaxies is that metallicity is not the primary driver, it seems, of IMF variability. It could also be related to more fundamentally to velocity dispersion. But then of course, these extragalactic IMF measurements really are inconsistent with the constraints we get from the Milky Way and the nuclear star clusters. And so I think we have a real problem on our hands where we have to figure out, is there something going on with the stellar population models that we don't understand, which seems unlikely to me because these IMF measurements are also being confirmed through just dynamical modeling, gravitational lensing, and we've done a lot of diagnostic tests. So if anybody's curious about this, I do encourage you to look at my 2017 B paper on this. And so it's really, so you know, what I'm trying to get at when I emphasize how important it is to try to establish these windows to the early star formation of these massive early type galaxies is, you know, was there something different about star formation that was happening either in whatever environment or whatever epoch these cores were forming that would cause these exotic populations like the variable IMF, the rapid star formation, the early quenching. And so I think what we've got right now is just a handful of problems. And so we need to figure out a way to establish these observational windows to try to see if we can come to some solutions. And that's where I think the globular clusters are really going to be key.
Thank you.
Any other? Oh, go ahead.
No, I'm just saying that maybe we should probably wrap up since our chair has already left. So I don't know if there are other questions.
Again, I'm around. You can message me in on the Microsoft Teams app or email me. Again, I really am looking forward to working with more people, and so I'm you know, very happy and eager to hear from people here.
We have the Jamboree on Friday. Am I right? Can somebody confirm that?
Yeah, I think I saw that the Jamboree is happening on Friday.
Yes, the Jamboree is on Friday.
Okay, wonderful. So I guess you see everyone on Friday then?
Mm-hmm.
Thank you very much.
Well, thank you, everybody, and thanks for bearing with me as I ran over time. I am sorry about that.